Our first speaker is Professor Colin O'Halloran from D-Risk Limited. He's the technical director there. He's an international authority on critical software and systems. He has been involved in the development and use of formal verification techniques for 30 years and includes the independent verification Typhoon flight control system software. He is now a founder and a technical director at D-Risk.
So what I'm going to be talking about is the verification of systems which have swarm intelligence, but I will take an aside to address the issue about AI on board a particular system. First of all, I think it's worth talking about what we mean by emergent behavior. I don't know how many people are familiar with John Conway's Game of Life, but it's something the mathematician John Conway invented back in the early 1970s. And it consists of a cell on a grid, and it follows 4 simple rules. For population, each cell with 1 or 0 neighbor dies, as if by solitude. Each cell with 4 or more neighbor dies, as if by overpopulation. And each cell with 2 or 3 neighbors survives. So you either survive or you die. And the 4th rule is about population. For a space that's unpopulated, each cell with 3 neighbors becomes populated. So hence the game of life. This is the simplest form. Here's a single cell. According to the rules, it will die. However, the evolution of 3 cells in this configuration, this has 2 neighbors, so it will survive. These 2 will die. But of course, we've got the 4th rule as well, which is about these 2, which are unpopulated and become populated because they're adjacent to 2 or more. And that flips between the 2. So you have a stable configuration in terms of that starting initial point. So that's all very well. The point here are there are 4 simple rules to follow. And these are the sort of emergent behavior can arise from just following 4 simple rules. Here's an initial configuration as a starting point. 5 generations later, you get this pattern. 10 generations later, that pattern. 15 generations, another pattern. 20 generations, you're getting this new sort of formation occurring. Generation 26, it starts getting interesting in terms of that. So we focus down on the just 1 generation next. And then you get back to where you were before, so now it'll cycle. So you get all sorts of surprising emergent behavior just from following 4 rules and an initial configuration. So that's what I'm trying to get at in terms of emergent behavior. It's what I think is termed as weak emergence, as opposed to strong emergence like the mind. So here's some of the advantages of a swarm approach, and the ones I want to kind of focus on are it's decentralized. There's no central control. The same way as there was no central control in terms of those cells just following 4 rules. They just operated, lived, populated, died by following those 4 rules. And they're self-organized, so the solutions are emergent. So how do we go about assuring such swarms which are highly distributed, parallel, and emergent solutions occur? There's no central control. Well, it needs a little bit of a recap in terms of the approach that we take, technologies that we use. Now, traditionally, you start with software requirements, which you write in English, which is a very good place to start. And unfortunately, we're not so good at writing good English or good natural language. And a human has to do that. That's where the motivation comes from. And that's where we use our tool called Capture. So it's a tool for, forgive the pun, capturing requirements in English, or trying to encourage people to use English. Whether they do that or not is another matter. But it has an English syntax with a formal semantics. So there's an underlying formal language there as an intermediate language, and it basically compiles to a representation in a process algebra called communicating sequential processes. Now, you also have another human activity, which is to produce a design. In our case, we're using the de facto standard of design tools for Simulink and Stateflow, using control systems. And then what traditionally happens is you have a review by a human being, either by eyeballing it and thinking about it very hard, or by testing, doing simulation. And what we do is to replace that by a tool that we've developed called ModelWorks, which basically uses refinement model checking using CSP as its formal basis. And we have given a formal semantics to Simulink and Stateflow in order to achieve that. So we can do this automated comparison. And that's the key thing to do with formal methods, is that it can be done by a machine. Now, the motivation for our tools, and we heard a little bit about tool qualification this morning, is this section 4.4 of DO 178C, the Software Lifecycle Environment Planning. In particular, we want to choose requirements, developments and design methods and tools that limit the opportunity for introducing errors in the first place. So it's not impossible, but you want to start to constrain it to make it more difficult to do that, less opportunity. And indeed, for those errors that are introduced, that they can be detected through verification methods. So that's the whole philosophy about the way we are going. Now, that's all very well, but formal methods tends to have a very bad press in terms of it's gold-plated, it's expensive, it's time-consuming, experts are needed. But as we heard this morning about particular silver bullets in particular areas, they can be very effective. And this is a way you have some difficulty in terms of arguing about whether you have a better system at the end of using these type of tools and techniques as opposed to traditional or conventional means. Because when you're talking about 10 to the minus 6, 10 to the minus 9, it's empirically impossible to demonstrate before deployment, and sometime after deployment indeed. But what you can measure is time and cost, and a threshold in which you can meet and do at least as well as conventional methods such as testing. So here are an experiment that was set up in a project called Picassos. It involved Jaguar Land Rover, Johnson Matthey batteries, and Ricardo, de-risked there, and metrication experiment was set up by York Metrics. And this is for a hybrid system for a car. And there were 3 approaches. One was a conventional approach we used for ISO 26262. One was using a tool called SLDV, which is sold by the MathWorks, and one using de-risk's ModelWorks tool for Simulink and Stateflow, which was under development in terms of trying to expand and be able to accommodate the subset of Simulink and Stateflow used by Jaguar Land Rover and Ricardo and so forth. The first thing to notice is it's blind seeded with 48 errors. So we didn't know, or the people who were carrying out the verification didn't know where the errors were. They're completely separate. And then these were separate teams as well. So the fact that they able to, through testing, for example, discover errors, some of these errors, that was not available to the other teams who were using these other tools. So it was an expensive, time-consuming trial, but very worthwhile. A note, we don't have any figures for the use of ModelWorks for this particular one because the experiment time ran out for collecting metrics at that point. Here's another interesting thing. The same subsystem of the hybrid car was done independently by 2 different teams, one in Ricardo and one in Johnson Matthey batteries. And not exactly the same, but they're very close to the same sort of figures to give you a kind of indication of the validity of the approach. The other thing is that you notice that the use of SLDV costs more than conventional testing. And the reason for that is because of the size of the subsystem and the fact that you have to use SLDV and create your own assertions. So you have your requirement for the system, and you've got to break that down into assertions and place those assertions into the Simulink and Stateflow. which is great from the point of view that you really need to understand what the system is doing before the SLDV tool will say, tick, yes, I've automatically proven these assertions. So there's a lot of effort there to do that. So it's only until you get to larger systems you really start to see the benefit. However, in terms of model works, because we take this idea about choosing requirements at the English language level and automating that aspect, not having to plant assertions, you will get advantages straight away. So we were showing 80% savings in some cases, 60% in others, as for smaller systems, but benefit. And that is, has improved, if anything. So there's an economic reason for doing it. And not only did it find all 48 blind-seeded errors, but it found one which was unintentionally introduced by the people at Ricardo. Now, so we're going back to the swarming. So there's the technologies we've been using. These are some old results that we did in a Innovate UK project based on some work we did with L3 ASV, Autonomous Surface Vehicles. So here's a screenshot of being able to do it hasn't come out very well, but this is a way of putting definitions about your vocabulary, if you like, that you're going to do for your English requirements. And this is the sort of thing which you then can write. Now, the trouble is the tool allows you to write English requirements. The trouble is you don't necessarily bless with people who can write good English. So that can't, you still get a bit of like pseudocodey type stuff coming in there. But believe me, it can be made much nicer, but underpinned by formal semantics. And this is a particular example of a requirement of the alpha algorithm, I think it was, about how to progress and what happens when one individual boat becomes disconnected from the rest of the swarm. And this is the intermediate language that's produced. So it's still reviewable by a human being. You don't get to see the CSP, which will be incomprehensible to a human being. The results of that work, which were a few years ago, revealed a flaw in the alpha algorithm, which was known about, but in an attempt at the time published results. And we went on to verify the beta algorithm and explored aspects of fault tolerance. So the beta algorithm and alpha algorithms are swarm algorithms, and what they try to do is maintain swarm coherence, so that they're still moving through the system as a swarm, but they don't dissipate and they don't collapse in on themselves. And this is interesting aspect because of the swarm, but how you can use that. Some of the systems may become fail because of communication failures or whatever, and the swarm continues as it is supposed to do. We demonstrated that the requirements for an individual's contribution to the swarm could be captured in a comprehensible template language. And I've got a new version of Capture, which is much better than the one we used before, which allows you to guide the user in terms of writing, expressing these sort of requirements in a lateral language description. We used a specification to verify a low-level design, which could be directly coded from. So that's the definition of a low-level design. It's Simulink and Stateflow design, which you can automatically generate code from. So we verified the Simulink and Stateflow against the requirements for the algorithm, the swarm algorithm. And then we used the swarm algorithm requirements to verify the swarm property that we're interested in, the fact that it would be coherent. Now, this bit about the template language, natural language description, even if I criticize the use of English that the guys came up with, it's still better than this sort of formula, which you typically see. So every robot knows that eventually it will be forever connected to every other robot is more comprehensible than this sort of thing, especially if you're going to get it used by industry. Now, what here talk about is my recent work, investigating a compositional framework for swarms that guaranteed that desired swarm properties, like coherence, no matter what the size of the swarm is. And we've just actually last week defined our protocol as a way of a individual joining a swarm and maintaining the swarm property, the swarm coherence, or a shape, which is what I'll come and talk to you about. So this is evaluating this approach, this methodology. We're using this particular new swarm algorithm, which desired geometric shapes emerge from individual robot or drone behavior. And such shape is useful, for example, in military for radar reflections as a decoy. The swarm algorithm has been incorporated into the Simulink and stateflow design, and we verified using a verified collision avoidance system for BB loss. So I'll do a little diversion on this because this is meets the challenge that was set this morning about a high integrity, high availability architecture for being able to contain an AI decision making. So this is the vignette it's supposed to kind of basically do is avoid that sort of thing and do a definite maneuver for collision avoidance in the air. This was a flight trial, which was, I haven't got the video of this here. We have got video which shows about how this is coming in from this direction, detects it, takes an deliberate avoiding action as a human being would, turns back into try and get through, realizes it's still going collision path, takes the deliberate avoiding action, and eventually gets over there. And that was our first tranche of this, first drop, which we weren't expecting actually to be flown. Other pathological vignettes were put in terms of simulation. So here's something that's just going backwards and forwards, and it's being guarded in left and right. So what does the decision-making system do? Well, it does what a human being does. It climbs over, and goes around, and then goes back to the point which it needs to. So it did behavior which was safe and what a human being would be expected to do, but we weren't expecting ourselves. Back to swarming. So this is the shape algorithm I was talking about, and this was done through simulation. There's a paper concerning this, and basically the four were done diamond formation, because this is in 2 dimensions rather than doing a pyramid or something like that. Line formation, wedge, and column. We expressed the requirements of the algorithm using the risk capture tool again, formally verify the requirements of the algorithm against the specification of desired shape in 3D space. So basically, the intuition is we had an ideal shape, and we showed that as time evolved, it would converge to that shape and stay within a certain tolerance of that shape. Oops. And we formally verified the Simulink and stateflow design against the requirements of the algorithm. That's the key message. This is how we were able to decompose the problem into tractable verification aspects. Okay? This is just an example about how this is the BV loss part, and this is the rest that was added in to do the swarm algorithm for the emerging shape. And just an example of a simulation that we ran where a leader avoids an obstacle and they follow, but maintaining the shape. And that's it.
We do have time for one question. Yep, Paddy. I always rely on you, Paddy. Thank you very much.
Yeah, I listened to your talk about the language and specs.
Yeah.
And I was thinking from the parallels in the computing industry where there's lots of languages, and when people are talking about that kind of subject, they have pseudocode, which is not a particular language, but it will express what it is. Are you seeing, or is there a space for specs to have pseudo-spec, which is your kind of thing when they want to get into a bit more technical, but not specific, but they want to be a bit more specific when they're writing the specs? You know, do you start to see the spec writers bringing that kind of thing in?
So, in answer to your question, what we're trying to address is the certified regulator. It has to be comprehensible to them. So that's the key about writing good English and then relating it to a intermediate representation, which is what the textual form I was showing. But the tool guides you through the process of being able to make precise what exactly you mean by reversing course or whatever. It gives you the vocabulary in order to be able to make that link into what you might think of as a more pseudo-coded type of thing. But what we really want is something that is truly natural language, which a certifier can understand, and then through tool qualification and understanding of the process, get confidence that what's been designed and ultimately what's been coded satisfies those requirements.
Thank you. And thank you very much for Colin. Thank you, Colin. Thank you.